All right, good morning. We're going to look into the rest of the final review material. And again, just want to, first of all, just go into just a little bit of details we have regarding partial fraction decomposition. And again, this is going to be in Alex in the homework, but it will not be in your last exam. Okay, and just a couple of problems, and we have looking at what we have in terms of breaking down this fraction in terms of what we have of adding and subtracting or subtracting partial fractions. And we have for this item, okay, now we have 3x squared plus 4x plus 2 all over x cubed plus 2x squared plus 1. And we have in the denominator, okay, we have terms, okay, or an expression that can be factored. Okay, so right now we have 3x squared plus 4x plus 2. And we have all over now for x cubed plus 2x squared. And I tell you what, let me change that. Again, just make it factor friendly. Sorry about that. Okay, so I have x cubed plus 2x squared plus x. Now, greatest common factor we have here is x. And guess what? Upon factoring out x, we have x squared plus 2x plus 1. And guess what? This trinomial is factorable. Okay, so I have 3x squared plus 4x plus 2. I have all over x. Okay, and for x squared plus 2x plus 1, okay, now we're going to have that binomial x plus 1 times itself. And I'll just go ahead and put this in condensed terms. And now for x plus 1 squared, okay, you're going to have what is going to be referred to as a repeating linear factor. And for the partial fraction decomposition on this one, okay, what I'm going to do here is that we have for this ratio, so I got a factor with x, so I'm going to express what I have here with a over x, and for x plus 1 squared, what I'm going to do here is I'm going to set up a fraction. We're going to have b over the first order of x plus 1, and I'm going to keep applying powers to x plus 1 until I get to the original degree from the factoring. Okay, so I have plus c all over x plus 1 squared. Now I'll just give you like just a separate case. Like if I had something like 2 over x minus 1 to the third, let's say, and I wanted to break this up into partial fractions. Have like x minus 1 to the third. This is like a repeating linear factor with x minus 1. So we'll start out with a over x minus 1. Let's say you have 2x over x minus 1 cubed. So I have a over x minus 1, and then I go up from the first degree to the next degree. And I continue to do so until I get to the original degree. Okay, so I have c over x minus 1 to the third. Okay, so that's what that is all about with repeating linear factors, and that is with the square of x plus 1. Now, if I multiply the equation by the least common denominator, which in this case is going to be x and the square of x plus 1, and for what we're going to have here, we're going to have 3x squared plus 4x plus 2. You have all over x times the square of x plus 1, and again you have multiplied by both x and the square of x plus 1. Okay, so you want to have, for this original term, okay, so you want to have the denominator, okay, to completely cancel. So that means that we have both x and x plus 1 to the second to go out. Now, in the case of a over x, and we have multiplying by both x and the square of x plus 1. Okay. Now, it is going to be just x that will go out, but you'll have a to be distributed over the square of x plus 1. And we have, now for b over x plus 1, and multiplying by, again, x and the square of x plus 1, what's going to happen here is that you got b over a first order of x plus 1, but left over, you're going to have b times x times 1 degree of x plus 1 that will be left over. And as for c over the square of x plus 1, okay, so you'll have the square of x plus 1 to completely go out, but you'll still have c to be multiplied by x. Okay, so we have, upon clearing out the fractions, again, so I have in the rewrite, I have 3x squared plus 4x plus 2, and we have is equal to a times the square of x plus 1, and we have plus b times x times the quantity of x plus 1 and again for c, okay, now again the denominator in the square of x plus 1 completely canceled, but you still have the x factor that remains. Okay, so if you notice in this scenario, okay, we have three unknowns with a, b, and c, and but we have only 2 zeros that we can apply, okay, and that is going to be in the case of what we have from x and x plus 1. And let's say that if I solve for a first, so I can set just the x factor to 0, okay, and upon doing so, okay, so I have for x equal to 0, so we have 3 times 0 squared plus 4 times 0 plus 2 I have a times, okay, 0 plus 1 quantity squared and for what I'm going to have here, okay, so I got b times 0, so this will go out, c times 0, that will also go out. And guess what? So for what we will have left over, left-hand side becomes 2. And got a times the square of 1. So we have that 2 is equal to a. So you're going to have that a is equal to 2. Okay. So we have the value of a at 2. And in the case of, if I set x to negative 1, so if I go back to the equation setup, okay, so I have 3 times, okay, the square of negative 1 plus 4 times negative 1 plus 2. Guess what? So I got 8 times the quantity of negative 1 plus 1 to the second. So that's going to be zeroed out. I got b times negative 1 times the quantity of negative 1 plus 1. Negative 1 plus 1 is 0. Okay, that also goes out. we have plus c times -1. So right now we've got 3 times 1. 4 times -1 is -4. And we have plus 2. And right now we have is equal to -c. So we got 3 minus 4 is -1 plus 2 comes out to +1. So we have that 1 is equal to -c. And so it's going to turn out that c is equal to -1. Okay. And so just looking at the shape of things. Okay, so we got this particular ratio, and we have a determined as well as c determined, and I don't have any more zeros that I can apply, so I can just choose something arbitrarily. Okay, so I got a at 2, c at -1. Those are already known, and I need to select just a random value for x, okay, in order to create a pathway to solving for b. Okay, so I got 0, -1, and I'll just choose x equals 1. And something that's low digit, something I can easily substitute in for x. So if I were to choose x equal to -1, so we have here, I have 3 times the square of -1 plus 4 times -1 plus 2 and that is equal to, okay, so you got for a, you got 2. I'll get to that. So you have 2 at, it should be x is equal to 1. Don't know why I did -1. Okay, so you got x equal to 1. Okay, so you got 3 times, okay, the square of 1 you got plus 4 times 1 plus 2, and you have equal to a times the quantity. Okay, so you have 1 plus 1 squared. You got b times 1 times the quantity of 1 plus 1, and we have plus c times 1. Okay, so just fill again. So you got 3 times 1, 4 times 1 is 4, and we got plus 2. Now a again is at 2. 1 plus 1 is 2, which will be squared. And got b times 1 plus 1. Okay, so you're going to have b times 2, and c is at -1. So right now we've got 3 plus 4 plus 2. And we got 2 squared is 4 times 2 is 8. And we got plus 2b. And got -1. And we are narrowing it down. So we got 4 plus 3 is 7 plus 2 is 9. And we got 7 plus 2b. And if we take 7 away from both sides, okay, so you got 2 is equal to 2b. And in this case, right, we're going to have that b is equal to 1. So a we have at 2, b we have at 1, and c we have at -1. Okay, so we have, all in all, it's going to turn out that for what we have in the ratio, okay, so we have 3x squared plus 4x plus 2. We have all over x cubed plus 2x squared plus x, and that is going to be equal to, and we have for a over x, okay, that's going to be 2 over x. And we have for b over x plus 1, we're going to have plus 1 over x plus 1. And with c over the square of x plus 1, that's going to be -1 over the square of x plus 1. Okay, and so that will be the partial fraction decomposition of what we have for this ratio. Okay. All right. And again, we had x plus 1 to be a repeating linear factor. Thus, you had the separation going from the lowest degree in the natural number powers, where we have x plus 1 to the first, up to the original degree from the factoring. Okay. Okay, so we have, again, so you have three partial fractions from this particular ratio. All right, now just one more case here with partial fractions. Okay, and here we're going to have 6x squared plus x plus 2, and we have all over x cubed plus x. And if I look at expressing in factored terms, okay, so I have 6x squared plus x plus 2. Now for x cubed plus x, we have x times the quantity of x squared plus 1. Okay, and so just looking at what we have in the setup. Okay, so we got in this layout. Okay, we have with x squared plus 1. Now this particular expression cannot be factored, and with the second degree, this is what is referred to as a quadratic factor. And what you're going to do is that in setting up what we have in partial fraction decomposition terms. Okay, now we got, again, the linear factor at x. Okay, so we're going to have that bit of history to repeat in the initial stages. Okay, so we're going to have a over x. Now for x squared plus 1, okay, what you want to do is that you want for there to be, if the expression cannot be factored, you want for there to be a 1 degree difference between the denominator and the numerator. Okay, so you have, like with x squared plus 1, I want the numerator to be first order in x. So I'm going to have bx plus c. And let me give you just like an example. If I have something like x plus 1, and say we have x times, and we'll say 3x cubed and we'll say plus 4x plus 7. Now just kind of like with the partial fraction decomposition on this one, we have like a over x. Now as for the denominator here, which I cannot factor into integer coefficients, again, I want for there to be a 1 degree difference between the denominator and the numerator, higher by 1 degree in the denominator. So like for this one, I want the numerator to be second order. So I got bx squared plus cx, and I want the numerator to just go all the way down to a constant. Okay, so for what we have in this particular setup, okay, so I got a over x, and I have plus, once again, bx plus c over x squared plus 1. Okay, and just looking at what we have and setting things up so I can clear out the fractions. So multiply by both x and x squared plus 1. And we have, upon doing so, we have fractions to be cleared out. Okay, so here for the first ratio case, you're just going to have the denominator and all of x and x squared plus 1 to go out. As for a over x, multiplying by x as well as x squared plus 1. Okay, so we have x's to go out. And as for bx plus c, I have multiplying by both x and x squared plus 1. Okay, so you're going to have x squared plus 1s to go out. Alright, so you have in resetting. Okay, so I have 6x squared plus x plus 2. And we have is equal to a times, okay, the quantity of x squared plus 1. And multiplying bx and c by x, we have bx times x, so this will be bx squared. Then we have plus cx. Okay, and again we have 3 unknowns, and this time we have only one real 0 that we can use, and that is upon setting x to 0. Okay, so I have 6 times 0 squared plus 0 plus 2. Okay, and plugging in 0 for x. Okay, so both b and c are going to go out, and for what I have on the left, okay, left hand side I have it 2, and I got 0 squared plus 1 is 1 times a, so I have 2 is equal to a, so I'm going to have that a is equal to 2. Okay, and now for what I have, again I have only one 0 that I can utilize, and what I can do is just choose random values for x. Let's say if I choose x equal to 1. Okay, so I have 6 times the square of 1 plus 1 plus 2. Now a is known. So I have 2 times 1 squared plus 1 plus b times 1 squared plus c times 1. Okay, so we have 1 squared is 1, 6 times 1 is 6, plus 1 is 7, plus 2 is 9. And you're going to have 1 squared plus 1 is going to make 2, times 2 is 4, plus b plus c. Notice I have the terms b and c to remain. And what I can do here is that I can set up an equation, okay, from this. Okay, so if I take 4 away from both sides, I had that 5 is equal to b plus c. So I'm just going to set up an equation here. So I'm going to have that b plus c is equal to 5. Okay, I'm going to put this at bay for the moment. And then if I choose, let's say, x equal to 2, so I have 6 times the square of 2 plus 2 plus 2. And again, a is at 2. And for x squared plus 1, that's going to be 2 squared plus 1. And we have plus b times, okay, the square of 2. And we have plus c times 2. Okay, so 2 squared is 4. 4 times 6 is 24, plus 2 is 26, plus 2 makes 28. 2 squared is 4, plus 1 is 5, times 2 is 10. I got 10 plus 4b plus 2c. So I now have that 18 is equal to 4b plus 2c. So we have an equation here. So we have 4b plus 2c is equal to 18. And so just looking at what we have with these simultaneous equations. So if I line things up here, so I have b plus c is equal to 5. And I have 4b plus 2c is equal to 18. And what I can do here is just perform the addition method. And I'll just cancel out the c's and solve for b first. So if I just multiply the first equation by -2. And again, why am I doing this? And that is to be able to cancel out the c's and go ahead and solve for b. So we have -2b minus 2c is equal to -10. And you have 4b plus 2c, again, is equal to 18. So you have the c terms to cancel. So got -2b plus 4b makes 2b. -10 plus 18 makes 8. And we have that b turns out to be at 4. And again, I can plug 4 into either of these equations. Okay, so we have with b plus c equal to 5. So 4 plus c is equal to 5. And it's going to turn out that c is equal to 1. Okay. All right. So for what we have in the overall picture, okay, so we have, again, a is at 2, b is at 4, and c is at 1. And just for the partial fraction decomposition, okay, so I have, so a is at 2, so this would be 2 over x. And b is at 4, and if I plug 4 back into b, this is going to be 4x, and c is at 1. And so we have all together, so we have 2 over x, and then bx plus c is going to become 4x plus 1, and that is going to be all over x squared plus 1. Okay. So this will be the partial fraction decomposition breakdown of what we have in this ratio. Yeah. Okay, and again, that is not going to be in your final test, but it is in the ALEKS section 8.3. All right, and speaking of final exam, okay, if we look into the items that said to be working on, okay, from the pages, okay, and starting out with what we have from page 404, okay, and we got in the case of number 36, and just taking what we have now. And this goes back to logarithmic expressions, okay. Then we have for number 36. Okay, we have a natural logarithmic term. And we have of the fourth root of p times q and we have all over t to the third times m. And rewriting the radical in non-integer power terms. So again, we have with the fourth root of p times q. You can regard this as the fourth root of p. times, okay, the 4th root of q. And so this will be p to the 1/4 times q to the 1/4. Okay, so just taking what we have in this natural logarithmic term. Okay, so we have the natural logarithm. So I have p to the 1/4 times q to the 1/4. You have all over t cubed times m. Okay, so you got two factors, the numerator, 2 in the denominator, so you have multiplication and division going on simultaneously. And in expanding now, multiplication is going to imply addition, whereas division implies subtraction. Okay, and anything in the numerator will be attached to positive logarithmic terms. And if I take what's at the top first, then we have a positive natural logarithm of p to the 1/4, and we have followed by, let's say, a positive natural logarithm of q to the 1/4, and with t cubed m located in the denominator. And we'll be subtracting those respective logarithmic terms. So we have minus the natural logarithm of t cubed, and we have minus, okay, the natural logarithm of m. And again, rewriting the powers as coefficients. And so we're going to have here 1/4 of the natural logarithm of p. And we have plus 1/4 of the natural logarithm of q. And we have minus 3 times the natural logarithm of t. And we have minus the natural logarithm of m. Okay, so everything has been separated, and again, all the exponents have been converted to coefficients. Okay, and if we take what we have in the case of number 47, okay, and we're looking at combining as a single logarithm. Okay, and so we have here, okay, so you have the base 15 logarithm of 3. And we have plus the base 15 logarithm of 5. Again, addition implies multiplication whenever you're compiling as a single logarithmic term. So I have the base 15 logarithm of 3 times 5. So now I had the base 15 logarithm of 15. Now we don't have any power explicitly expressed. Okay, but you read just 15 in the base as like 15 to the first. And base a log of a to the x goes to x, where in this particular case your x value is going to be at 1. All right, now for what we have in the group, looking at combining as a single logarithmic term, okay, and we have in number 61, okay, so we have 6 times base 10 log of x, and we have minus 1/3 of the base 10 logarithm of y. And we have minus 2/3 the base 10 logarithm of z. All right, and looking at compiling together. Okay, so any coefficients I have at the front, okay, the absolute values would be powers to which the attachments will be raised. Okay, so we have for the first term 6 times the base 10 log of x. This would be the base 10 logarithm of x to the 6th. And we have minus, okay, the base 10 logarithm of y to the 1/3. And we have minus, okay, the base 10 logarithm of z to the 2/3. Okay, so this time looking at putting together as a single base 10 logarithmic term. Okay, so the coefficients have been converted to exponents, and then just looking at what we have now. Okay, so the first term is positive, so this will signal that x to the 6 goes at the top, whereas the last two logarithmic terms are negative, so we have the attachments. We have a y and z, those will go on the bottom. And another way that you could express this, I'm just going to mention, okay, so you have y to the 1/3 times z to the 1/3. Let me just mention, or times z to the 2/3. In radical terms, so you have like the cubic root of y times the cubic root of z squared. And since you have the same type of root, you can go ahead and squeeze together. So you have the cubic root of yz squared. Okay, so we have another way that the result could be expressed is where we had the base 10 logarithm of x to the 6th. We have all over the cubic root of yz squared. Alright, and then now for what we have in the case of where the equations will come in, and we have for the group I mentioned, okay, from starting on page 416. Okay, and we have in the case of number 14. Okay, so we have an exponential equation, and we have here, okay, so we're looking at 27 to the x minus 4, and we have is equal to 9 raised to the 2x plus 1 degree. And so for what we have in the setup, okay, so we're going to have an equation that has a common base, okay, which is going to be at 3. And for 27 to the x minus 4, so 27 is going to be 3 cubed. And we have to the x minus 4. And for 9, okay, 9 is going to be 3 squared. And this will be taken to the 2x plus 1 degree. And again, we have with the power property of exponents. So again, I'm going to multiply the powers together on each side. Okay, so to the left I have 3 times the quantity, or 3 to the 3 times the quantity of x minus 4. So this is going to be 3 to the 3x minus 12. And to the right, we have 3 raised to the 4x plus 2. And so I have single base 3 terms. And I can go ahead and set the powers equal to each other. And just gathering together, okay, what we have in x and separating from the constants. Okay, so I have the higher x expression to be at 4x, so I'll just take out the lower. So I take 3x away, and for the constants, I'll just take 2 away. And we have negative 12 minus 2 becomes negative 14. And 4x minus 3x is x. So the missing value that we have in x comes out to negative 14. Okay, now for what we have in the case of, let's say for number 18, okay, this is a case of an exponential equation that does not share a common base. And here, okay, we have in the case of 18, okay, we have 2 to the x. Remember that 2 to the z is equal to 70. And there are various ways you can go about this. Okay, so we got the variable we were solving for on one side of the equation. And so this will give us, on the basis of taking the base a log of a to the x, I can just apply the base 2 logarithm on both sides here. Okay, so base 2 log of 2 to the z, that will go to z. And we had that z is equal to the base 2 logarithm of 70. And here I can apply the change of base formula, where I can take either the ratio of base 10 or natural logarithms. So z is going to be the natural logarithm of 70 all over the natural logarithm of 2. And if I take to the nearest 4 decimal places, okay, so I have the natural logarithm of 70 all over the natural logarithm of 2. And so you have for z, okay, so I have 6.129, okay, and then you got 28. So the 8 signals that the 2 to the left is going to be rounded up if I take the resultant z to the nearest 4 decimal places. And so you got your exact and decimal result, okay, where the decimal have to the nearest 4 places at 6.1293. And now in the case of what we have with number 20, okay, this is kind of another equation where we have no common base to be shared. And now we're looking at solving for y. And so we got 801 is equal to 23 to the y plus 6. Or 23 to the y followed by the addition of 6. Okay. And so if I look at isolating the y term, so I can take 6 away from both sides. So I have 801 minus 6, so this will be 795. Is equal to 23 to the y. And I tell you what, I can just swap, kind of do the commutative switch around, going from b is equal to a is equal to b format, and just rewrite this as 23 to the y is equal to 795. And just to take care of the base 2, like what I did to take care of base 2 and 18, I can take care of 23 if I take the base 23 logarithm on both sides. Okay, so left-hand side becomes y. And for the base 23 logarithm of 795, I could apply ln again, but I'll just go with log. It's still going to be the same value. Okay, so for what we have here, so you got the base 10 logarithm of 795 divided by the base 10 logarithm of 23. Okay, and so it looks like we're going to have y to be at 2.1299. And that second 9 does not round up, thanks to the 1 that is alongside it. Okay, now for what we have in the case of the next item, and we have this one, it's kind of an outlier, but we do have for number 32. Okay, so we have an equation here, so we have e to the 2x minus 6 times e to the x minus 16 is equal to 0. Okay, and in its own way, this is a quadratic equation. And what this means is like for like e to the x times e to the x. You have e to the 2x, so these you have factoring out to e to the x separately. And then we have with minus 16, okay, then we have e to the x plus 2 times quantity of e to the x minus 8 is equal to 0. And setting each of the factors to 0 upon using the zero product property. Okay, so I have e to the x is equal to negative 2. For e to the x minus 8 is equal to 0, I have that e to the x is equal to 8. And guess what? So I can take care of the e if I take the natural logarithm on both sides. Okay, so natural log of e to the x. Again, you have a base e logarithm of e to the x. So this will go to x. I got x equal to the natural logarithm of negative 2. But again, to be defined, the attachment has to be a positive value. And because of this, for this attempt at x, there is no solution. It's because of the negative. Whereas in the case of what we have with the next, okay, we have x is equal to the natural logarithm of 8. 8 is positive, and there's going to be a solution on this. So we have x equal to the natural logarithm of 8. And if I were to take this to the nearest 4 decimal places, so this would be about 2.0794. Okay, so there's only one solution for x. That's with the natural logarithm of 8, again, which would be about 2.0794. Okay, and then we have looking at what we have for logarithmic equations. And we have for number 40. Okay, so we have the base 10 logarithm. And we have of the quantity p squared plus 6p is equal to the base 10 logarithm of 7. And again, whatever we have for p squared plus 6p, okay, that must be positive. Okay, if you notice, both sides, okay, have are in the same base, and I can go ahead and set the attachments equal to each other. So I have p squared plus 6p is equal to 7. Now we have a quadratic equation. So we have p squared plus 6p minus 7 is equal to 0. And if I look at factoring, okay, so we had the quantity of, looks like p plus 7 times that of p minus 1 is equal to 0, and looking at setting each of the factors to 0. And so we have with our attempted solutions at negative 7, if I plug in, square of negative 7 is positive 49. 6 times negative 7 is negative 42. 49 minus 42 is positive 7. That checks out. 1 squared is 1. 6 times 1 is 6. 1 plus 6 is also a positive 7. So both of these solutions do check out. So the values in p that will make this equation true will be negative 7 and positive 1. And we have now for the case in number 42, okay, and here We have another logarithmic equation. This time we have in the base 6 logarithm. Now we've got 5 times the base 6 logarithm of the quantity of 7w plus 1, and we have plus 3 is equal to 13. Okay, so I can start things off. Okay, so I can take 3 away from both sides. And let me just make sure I get too far ahead. Okay, so 7w plus 1, MBP must be positive. So we have 5 times, okay, the base 6 logarithm of 7w plus 1 is equal to 10. And if I divide the equation by 5, okay, so this will come down to, for right now, we have the base 6 logarithm of the quantity of 7w plus 1 is equal to 2. This stemming from 10/5. Now I have a single base 6 logarithmic term, and now I can take the a to the base a logarithm of x is equal to x property. So I can now treat both sides as powers to which the exponential base 6 is going to be raised. Okay, so left-hand side, okay, this will become 7w plus 1, and 6 squared becomes 36. And just looking at taking away 1, and we have that 7w is equal to 35, and we have a division by 7. Okay, we have an apparent solution with w equal to 5, and just looking at what we have here with w at 5, 7 times 5 is 35 plus 1 is 36, and 36 is positive, and so we do have 5 as the unique solution in w. And then we have, in the case of number 47, okay, this one, okay, we're looking at a natural logarithm. And here we have 2 times the natural logarithm. And we have of the quantity of 4 minus 3t. And we have followed by the addition of 1 is equal to 7. Okay. And again, just like 7w plus 1 has to be positive, okay, whatever we have for t must ensure that 4 minus 3t be positive as well. Okay, and we have for this equation, if I take 1 away from both sides, okay, so I have 2 times the natural logarithm of the quantity of 4 minus 3t. Okay, that is equal to 6, and I can take care of the coefficient 2 upon dividing. And just looking at what we have now, okay, so this comes down to the natural logarithm of 4 minus 3t is equal to 3. And to take care of the ln, okay, remember, you got ln is going to be a base c logarithm. And again, to take care of the natural logarithmic base, okay, we can treat both powers, or both sides rather, as powers to which e can be raised. Okay, so for what I have on the left hand side, okay, so this will go to 4 minus 3t. Okay, that is equal to e to the third. And looking at taking 4 away from both sides, okay, so I have negative 3t is equal to e to the third minus 4. And for t, okay, now in exact terms, so t is equal to e to the third minus 4 over negative 3. And as a decimal approximation case, so I have with e to the third minus 4 e to the third minus 4, that's the number that's just over 16, and dividing by negative 3. So to about the nearest 4 decimal places, this will be about a negative 5.3618. And you can go back and check, okay, so we have, so we have whatever I have for 4 minus 3t must be positive. Guess what? Well, t is a negative. Well, a negative times a negative is a positive, and a positive additive 4 is going to be positive. So t is going to be this rather unusual value. You have e to the third minus 4 over negative 3. And as a decimal, okay, you have about negative 5.3618. All right. And very tricky one here. Now, for what we have in the case of number 49, okay, this is one where looks like some double checking is going to be required once again. Okay, now we have here, okay, so we got in the variable w. Okay, so I have the base 2 logarithm of w minus 3, okay, is equal to the negative of the base 2 logarithm of w plus 2, okay, and if you notice here, okay, we have logarithmic terms, okay, whereupon we have the base 2 logarithm of w minus 3 is equal to the negative of the base 2 logarithm of w plus 2. And this is kind of tricky here. And what I want to do is kind of do some things simultaneously. I can combine the logarithmic terms again, this problem is a little bit of an outlier. So get the base 2 logarithm of w plus 2 out, and what I'll do here is I'm just going to move the 3 over by adding. And let me just mention, okay, so w, whatever I have for w, I want both w and w plus 2 to be positive. Alright, so we have in the rewrite, okay, just swapping base 2 logarithm of w plus 2 and 3. So right now we have the base 2 logarithm of w plus the base 2 logarithm of the quantity of w plus 2 is equal to 3. Okay, so I have 2 distinct base 2 logarithmic terms, and I can make into a single term, again, where addition is going to imply multiplication. Okay, so we have the base 2 logarithm of w times w plus 2 is equal to 3. And just multiplying together. So w over w plus 2. Okay, that is going to be w squared plus 2w. So I have a single base 2 logarithmic term. And if I take care of the base 2 logarithm, I can treat both sides as powers, to which the exponential base 2 is going to be raised. Okay. So on the left-hand side, okay, we'll have w squared plus 2w is equal to 8. So I have a quadratic equation. And if I write this in standard form, so I'm going to have upon factoring, okay, so I have w plus 4 times the quantity w minus 2 is equal to 0. And as for what we have in the case of w plus 4 equal to 0, we have that w is equal to negative 4. We have that w is equal to 2. Now looking at what we have with the restrictions. Okay, so if w is negative 4, well guess what? The restrictions will be that w and w plus 2 must be positive. And guess what? Negative 4 falls short because negative 4 is negative. Negative 4 plus 2 is also negative. So negative 4 is going to strike out. Whereas with 2 is positive. 2 plus 2 is 4, also positive. So in this equation, there's only going to be one solution. And that is going to be with w equal to 2. And then we have crossing over, okay, to what we have again with logarithmic equations. And we have for number 50, okay, and we have on this one, okay, so we have with 50, okay, so you have the base 3 logarithm of y plus the base 3 logarithm of the quantity of y plus 6, okay, is equal to 3. Again, whatever I have for y and y plus 6 must be positive, okay. And again, in this arrangement, okay, so we have base 3 logarithmic terms added together. And if I look at making into a single statement, again, addition implies multiplication. Okay, so I'm going to be multiplying together in the consolidated base 3 logarithmic term the attachments y and the quantity of y plus 6. So we have the base 3 logarithm. I have of the quantity. Okay, so I have y squared plus 6y is equal to 3. And now I have a single base 3 logarithmic term, and I want the base 3 log to vanish. So I can apply, again, both sides as powers to which the matching exponential base is going to be raised. So we have 3 to the base 3 logarithm of the quantity of y squared plus 6y is equal to 3 raised to the third power. So the left-hand side, and we have that y squared plus 6y is equal to, and 3 cubed is going to be at 27. And setting this up as a quadratic equation in standard form, So I'm going to have y squared plus 6y minus 27 is equal to 0. So looking at factoring, we have the quantity of y plus 9 times that of y minus 3 is equal to 0. And we have y plus 9 is equal to 0, so we're going to have that y is equal to negative 9. And for y minus 3 is equal to 0, okay, now we have an apparent solution with y is equal to 3. And just checking what we have here, we have with y at negative 9, and the restrictions are that both y and y plus 6 be positive. Well, negative 9 does not meet the criteria. Okay, and in case of 3 is positive, 3 plus 6 is 9, also positive, so y equals 3 checks out, and that is going to be the only solution for what we have in the case of problem 50. Okay. And now, and just looking at what we have in the case of number 54. Yes, there's like one solution. Okay, again, that was at y equal to 3. Okay, now for number 54, okay, this time we have we got the base 2 logarithm of x. So the base 2 logarithm of x, okay, and I have is equal to 4 minus the base 2 logarithm of the quantity of x minus 6, okay, and once again, whatever I have for x as well as x minus 6, okay, those attachments must be positive. And if I look at combining together, okay, the base 2 logarithmic terms, I have that of x by itself. And I'll just move the base 2 logarithm of x minus 6 by adding on both sides. Okay, so I now have the base 2 logarithm of x plus the base 2 logarithm of the quantity of x minus 6, okay, is equal to 4. And once again, I have addition, and once again, addition implies multiplication. So we have the base 2 logarithm of x times, okay, the quantity of x minus 6. Again, I have is equal to 4. And then we'll have the base 2 logarithm, okay, we have of the quantity of x squared minus 6x is equal to 4. And taking care of the base 2 logarithm by applying both sides, again, as powers to which the base 2 will be raised. Okay, so we have the x squared minus 6x is equal to 16. And for what we have in following through, okay, so writing as a quadratic equation in standard form, okay, so I have x squared minus 6x minus 16 is equal to 0. And just looking at what we have here, once again, applying the zero product property, if I set x plus 2 equal to 0, okay, we're going to have the x is equal to negative 2, but guess what? X and x minus 6 must be positive, and negative 2, okay, that value strikes out. And for what we have in the case of x minus 8, if I set this equal to 0, we're going to have that x is equal to 8. X at 8, 8 is positive. 8 minus 6 is 2, also positive. So 8 is going to check out. So in number 54, there's only one solution, and that is going to be with x equal to 8. And we have, in the case of number 59, or number 59, okay, so this one, okay, we have in the variable m, okay, so you have a base 8 logarithm. Okay, and we have of the quantity of 6 minus m, and we have plus the base 8 logarithm of negative m minus 1 is equal to 1. Okay, and once again, whatever I have for 6 minus m and negative m minus 1, okay, these have to be positive. Okay. And just looking at putting together what we have here, so we have the base 8 logarithm, and again, we have addition implies multiplication of the attachments. And see what we got here. So we got the base 8 logarithm. So it's like we're going to have negative 6m minus 6 m squared. Yeah, we'll just do this. Okay, so you have negative 6m minus 6 plus m squared. Negative m times negative 1, that's plus m. And it's equal to 1. And just rearranging things. Okay, so you have a base 8 logarithm, so you have m squared, and so we got negative 6m plus m, that would be a negative 5m. I got minus 6. We're going to have this equal to 1, so I have a single base 8 logarithmic term, and I can, again, take care of the base 8 log appearance upon treating both sides as powers, of which the exponential base 8 is going to be raised. Okay, so for what do I have on the left? Okay, I'm going to have m squared minus 5m, okay, minus 6 is equal to 8. And then we have taking 8 away from both sides. So we have m squared minus 5m minus 14 is equal to 0. And looking at factoring, so I have, looks like m plus 2 and m minus 7. Again, with the zero product property, if m plus 2 is the zero factor, we have an apparent solution with m at negative 2, and with m minus 7 equal to 0, we have an apparent solution with m equal to 7. And just going back and checking what we have here. Okay. And okay, now this is kind of tricky. Okay, now we got m at negative 2. Now 6 minus negative 2 is going to be 6 plus 2, which is 8. That is positive. And with m at negative 2, well, guess what? You got negative m, and the negative of negative 2 is a positive 2, and 2 minus 1 is positive 1. So negative 2 is going to check out. But with m at 7, guess what? 6 minus 7 is negative 1. That already strikes out. And then you have the negative of 7 minus 1, which is going to be negative 8. So there are cases where the apparent solution that checks out is going to be a negative value, and that which you think is going to be a solution because it's positive, it turns out that upon inspection it will not. So in the case of 59, kind of tricky, but it turns out that the lower value in m is going to be that which will end up checking out. And so we have, for the solution, we're going to have that m is equal to negative 2.